So our second method for determining the delta H of a reaction is using something called Hess's law. And in Hess's law, we're going to kind of build the reaction we're going to make and determine the delta H for by being given other chemical reactions, and we're going to manipulate them. It's kind of a putting puzzle pieces together. If you like a puzzle and you like putting together pieces of the puzzle to construct something that you're trying to produce, then you'll kind of like this method. I love puzzles. I like this method. Now I want to give you the nuts and bolts of it. There's some pretty challenging puzzles out there for you to construct. But let's talk about the foundation of Hess's law. We're going to be utilizing these concepts here, relationships involving delta H. This is manipulations to a thermochemical equation. We know that if we double an equation, we would double the delta H. If we half an equation, we would half the delta H. So whatever we do to the coefficients, we do to the delta H. We also learned that if you reverse a reaction, it changes the sign. If it was exothermic going this direction, it's going to be, when you flip it around, an endothermic reaction. So those are the relationships we have to use to do this. Here's the statement of Hess's law. Hess's law says it doesn't matter whether you do a reaction in one step or a series of steps, the amount of energy change would be exactly the same, okay? Give you a non-chemistry relationship because it's a state function. I talked about volume and delta V, and if I poured a glass full of Coke into a glass, and I had 12 ounces in there, and I wanted to measure the change in volume, I could sit there and I could drink, and take it down to 6 ounces, and I know the delta would be 6, so that'd be one process. Or I could drink an ounce and I could set it down and I could come back, and I could drink 2 more ounces and set it down and I come back. I could drink 4 ounces and say, oh, that's too much, and spit some more back in and finally get there, and that would be doing it in a whole series of steps. So it doesn't matter what the change in volume is, whether you do it in one step or a series of steps. So this tells us this idea of being a state function. It is path independent. It doesn't matter how you get there. And we utilize this for coming up with a delta H of a reaction. Okay? So if you can take a chemical equation and express it as a sum of other equations, we're doing this reaction, this reaction, this reaction, they all add up to give me an overall reaction that I'm looking for, then whatever the delta H of all those individual reactions, if we sum them up, it would be the delta H of the overall. Going back to the volume example, let's say I drank 1 ounce. Oh, I started out with 12 ounces. I drank 1 ounce. Then I came back and drank 2 ounces, and then I came back and I drank 3 ounces, and when it was all said and done, I had 6 ounces left over. If I drank it all at once, that would be 6 ounces. If I drank a little bit, a little bit, and a little bit, that would get me down to 6 ounces. I could either add up all those, or I could do the whole fell swoop. That's what we're going to utilize with Hess's law. The easiest way to see this is be given an example. So let's look at an example here. I have several chemical reactions given to me there, and I'm trying to construct the bottom one. So I'm going to build this puzzle with the pieces. So we're going to just try to find those components and write them down. So let's start with, look at the bottom of this screen here, we need 2 carbons, and that Gr stands for graphite. I need 2 carbons in the form of graphite. Well, if I go up there and look at the first equation, I see that I have carbon in the form of graphite, but it's only 1. So let us double that whole reaction. That'll give me 2 carbons in the form of graphite. I'll write it as Gr. Okay, I'm doubling the whole thing. So I have 2 oxygen gases, and that is producing for me 2 carbon dioxide gases. So there is that thermochemical equation. And if I want to know the delta H of this reaction, which I do, it's going to be 2 times what it was before. So it's 2 times a negative 393.5 kilojoules. So I got now the first piece in there. Now that brought a lot of other stuff that I didn't want, but it got this graphite in place. Now I go to the H2. As I go to the H2, I see that H2 is in the second equation. And there's only 1 mole of it in the second equation, and I need 3 moles of it. So I'm going to take that second equation and I'm going to triple it. Okay? So I have 3 H2 gas. I have 3 halves O2 gas. And that is producing 3 H2O liquid. Now make sure that you're writing your substances down. The reaction, so I have to triple the delta H that's given to it there. So it's 285.8 kilojoules. I just tripled that value. So that gives me the hydrogen in place. The next thing that I need, and let me stop here for just a minute. It's going to be hard for you to hear and remember this because we're not seeing it as an example right now. But sometimes as you're trying to build and construct a reaction, let's say that there was some oxygen in that bottom equation. And I look up there and I see that oxygen is in all 3 of those equations. If you have a substance down there and it appears in more than one of the equations that's given to you, just skip over it, because it'll work out in the end. It'll cancel things out the way it needs to give you the amount that you want. But we don't have this going on here, so let's go ahead and construct the next component I need is the C2H6. So I see the C2H6 is in the 3rd equation there, and I see that it's on the left-hand side of the equation, but I need it on the right-hand side of the equation. So I know I have to flip the equation, and I also have too much. I only needed 1 mole, and that equation has 2 moles. So I'll flip it and cut it in half. So flipping it puts the carbon dioxide over here. Cutting it in half gives me 2 moles of it instead of 4 moles of it. The next thing that it has is the water. Cutting it in half gives me 3 moles of water. Okay. Then on the product side, it was what's written over there as a reactant. Now it's a product. Cut in half, it would be C2H6. And this is a gas. Cutting the 7 in half is 7 halves. Okay, and that is the O2 gas. So what do we do with the delta H? The delta H of the reaction, we have to cut it in half. Okay, so that's divide by 2 or multiply by 1/2. Cut it in half and change the sign. So it's going to be a positive 3119.6 kilojoules. So now I have all of the reactions that I needed to get the components in place. Now a lot of students just kind of do this and manipulate it and don't do what I'm suggesting to do next. And I really think that it will save you a lot of mistakes if you will go ahead and do this step. Make sure things cancel and leave you really with what you're looking for. So I see H2O as a liquid over here and H2O as a liquid over here, and it's both got a 3, so those can cancel. If this was a liquid and this was a gas, they couldn't cancel. They have to be in the same state. Sometimes you'll find that you'll have to add equations in just to get rid of some of these things that you had to add in by making this reaction. But we don't have to in this case. What else do we see? I have 2 carbon dioxides and 2 carbon dioxides. They cancel. All right, I have 2 plus 3 halves. That's 2 plus 1.5. That's 3.5 oxygens over here. And 7 halves is 3.5 also. So I have 3.5 oxygens over here, 3.5 oxygens over here. So all the oxygens cancel. And that does leave me with 2 carbons in the form of graphite, plus 3 hydrogen gas, that's a 2, producing C2H6, and that's a gas. So what do we do with all of these guys? Well, we add them together, being very careful that we're looking at our signs. This one's negative, this one's negative, this one's positive. And when I do that, I have a negative 2598.8 kilojoules. No, I don't. I'm looking at the wrong problem. Let's scribble that out. I have a negative 84.6. Okay, so that is the delta H for the reaction that I have right here. So that's Hess's law, seeing the equations, manipulating them to form the equation you're looking for, adding the delta H's to get the delta H that you're looking for. Okay, now you get to try one. Here we go. In this case, we have what you're trying to build is the top equation written there. You're going to use the ones below it in order to construct what you're trying to make and come up with one of those answers. See what you come up with, pause it, come up with an answer, and then resume. All right. Did you get C? If you did, then you did the right thing and you got the right answer. For B, you forgot to cut that reaction in half, okay? There was one of those reactions you needed to cut in half. Which one? Well, it was the one that had the CaO in it, the bottom reaction. I only needed 1 mole, okay? Forgot to cut that in half, so look at your work and see if you forgot to do that. If you picked at D, you forgot to reverse, therefore you forgot to change the sign of the second reaction. You need it flipped in order to change the sign. If you've caught your mistakes and you're done and you can move on. If you didn't catch your mistakes, then you might want to linger with me here and we will work it together at the top of this board, and let's choose a different color, okay? So you're still with me because you don't quite have this one down. Let's see, we've got to get calcium oxide on the left-hand side. The second equation has calcium oxide on the right-hand side and too much of it. So I'm going to flip the equation and put the calcium oxide over here, and I'm cutting it in half at the same time. So it's going to have 1 calcium, and it's going to have 1/2 oxygen. Okay? What's the delta H? Well, it's going to be the delta H that we see for that reaction, but I flipped it, so I'm going to make it positive. So it's positive 1269.8. 1269.8, that's positive, and it's kilojoules. Okay, I'm kind of running into those pink letters there. And I had to cut it in half because I cut the reaction in half. So that gave me the calcium oxide I was looking for. It also brought some other things in that I didn't want. The next thing I need is the carbon dioxide. The first equation has the carbon dioxide I needed, so I will write it as I see it. It's on the correct side of the equation. The correct amount is sitting there, so that gives me the Ca solid plus the carbon dioxide gas, okay, plus 1/2 of an oxygen gas, and the product for this reaction is going to be calcium carbonate, CaCO3 solid, and the delta H will be the delta H exactly as I see it because I used the equation exactly as it was played out there, 812.8 kilojoules. Now you take the time to make sure things cancel. I have 1/2 of an oxygen, I have 1/2 of an oxygen. This is on the left side of the arrow and this is on the right side of the arrow. I have a calcium on the right side of the arrow and a calcium on the left side of the arrow. That leaves me with a calcium oxide solid plus carbon dioxide gas producing calcium carbonate solid. So if these add up to give me this, then these add up to give me the delta H of this reaction, which is the negative 177.9. So that is utilizing Hess's law. These are the most straightforward ones. We'll work on some more challenging ones together in class.